And then that's zoom in and that's zoom out.
Awesome.
Okay? So, this symbol right here stands for what we call water potential. Can you say water potential?
Water potential.
And water potential, that means the potential energy of water. You see, water has a potential energy to it. Just like when I hold this pen up, it's got potential energy. If I let go of it, it's going to start racing downward, and that potential energy will be converted to kinetic energy. Y'all remember learning about this in physical science?
Yes.
Water has potential energy too. When water's just sitting there, that water can move somewhere else. Just like this pen can fall, the water can move somewhere else if it is in a spot where it's next to a hypertonic solution. A hypertonic solution has a lot of sugar in it, right? Sugar or salt. And the water, if you have pure water here, let's look at this situation. Let's say we have a cell, and there's pure water here, 0.0 molar water, and the cell, let's say, is 0.1 molar, a 0.1 molar cell. Here, I'll put a nucleus. What's the water sitting here going to do?
Go into the cell.
It's going to go into the cell. Do y'all remember that from yesterday?
Yes.
And the cell will swell up?
Wait, won't it go the other way?
No, because this is pure water right here. Water always moves from high concentration to low concentration, so it goes that
I
way.
watched a video of the cells blowing up.
So the cell will swell up, right? So this water has potential energy. If you put it next to water, an area that has less water, it'll move in that direction. And so we can calculate the water potential of a certain amount of water to see how that water will move. And that's what these water potential equations are for calculating water to see how it moves, calculating the potential energy of water to see how it moves. Now they give you, and they're going to give you these equations on the final, on the AP exam. They give you the equations you need. They're right here on the left of the handout. Water potential equals pressure potential plus solute potential. By the way, if you're wondering what this thing that looks like a pitchfork is, that's a Greek letter. You know what letter that is?
George.
It's the Greek letter psi. Do you know the Greek alphabet?
I thought psi was wait, that's phi.
That's psi.
Phi is the O with like this, the line through it.
You want to hear the Greek alphabet in less than 5 seconds?
Sure.
Alphabet again says the government news on proper omega.
Ta-da.
We had to get in the fraternity house. We had to say the Greek alphabet 5 times while holding a burning match.
You're in a frat, bro?
Yeah, I was in Chi Phi. Alphabet again the government news on proper omega. I got real good at saying it real fast.
Say it 5 times before the match.
Yeah. So I would strike the match, and they'd be like, say it, and I'd be like, I'm betting I don't know.
What did you have to do if you didn't get it?
It burned your hands. Okay, so those were the days.
Probably a lot more than that.
Hazing in college, but let's move on. So, what do these things mean? Well, the pressure potential, there's 2 things involved that are involved in how water moves. One thing is the difference in the amount of solute. And the solute potential is this part of the equation. Another thing is the pressure. Pressure, see, this water will move into this cell, and this cell will expand. But eventually pressure will build up, especially if it's a plant cell. Did I tell you that plant cells have cell walls?
Yes.
Y'all remember that from yesterday?
Yes, we do.
And the cell will swell up, but once it reaches the cell wall, it won't swell anymore. And the water won't be able to go in as easily because there is a pressure potential too. And the water pressure that builds up will keep the water from moving in. So there are 2 things to consider when you're considering water movement. you have to consider the solute, the amount of dissolved substances, and you have to consider the pressure, how much water pressure is built up. And I'll show you how to figure out these two things. It's two simple equations. This is the first equation. And the second equation is just for figuring out the solute potential. And usually that's what you do first in these problems. You figure out the solute potential first. So, I'll show you the solute potential equation. Solute potential equals negative ICRT. They give you these equations. They're up there on the top left.
We'll get it on the exam too.
Yeah, they give it to you on the exam. They give you an equation sheet. Okay? Now, first thing you want to know is what all these letters stand for. The letter I is called the ionization constant. And, yeah, that's it. The ionization constant is going to be a number that for us it's always going to be 1 or 2. The ionization constant, I, equals 1 for sugar and 2 for salt. 2 for NaCl, salt. Almost every problem you get in biology with these uses sugar, like glucose, some sort of sugar, one of these things, or salt. And what ionization means, do y'all know that NaCl, when you drop it in water, did you know it breaks up into Na and Cl?
Yes.
Do y'all remember that?
Yes.
Water will dissolve NaCl, Na is positive and Cl is negative, and those things will break up in water and be two separate things. That's why the ionization constant is 2 for sodium chloride, because it'll break up into 2 separate ions. That's why it's called the ionization constant. A sugar molecule does not break up into anything. It just stays as a sugar molecule when you drop it in water. So its ionization constant is 1. A glucose molecule will stay a glucose molecule when you drop it in water. It doesn't break up into a bunch of little things. So, simple enough, I is going to be 1 or 2 for all of our problems. And they'll give it to you in the problem what it is. Are y'all with me so far?
Yes.
C is the molar concentration. So for this cell right here, it's 0.1. C would be 0.1 molar.
Is it always going to
For
be
this
0.1?
cell, because they give it to you. No. If I said that this cell was 0.4 molar, then what would C be? 0.4.
Wait, why is it the one? It's always the one in the cell, not the water.
No, it's whatever they give you. So they might say a solution is 0.8 molar. Then if you're trying to figure out the solute potential for it, you plug in 0.8 molar.
Gotcha. Okay.
Okay? Now I want you to understand molar, M, is the same as moles per liter. Did y'all know molar is equal to moles per liter?
Yes.
You should know that from chemistry. R is a constant. What is that constant? They give it to you. 0.0831 liter bars per mole K. It's just a number to make this calculation work. Don't tune out. I know you're confused right now. It's all going to make sense in just a second. And finally, the temperature. T is the temperature in Kelvin. They'll give that to you in the problem. If we say that this is operating at 293 Kelvin, then you plug in 293. If they tell you that this cell is at 20 Celsius, do you know how to convert that to Kelvin?
Add 273.
You add 273 to convert it to Kelvin. And that's 293 Kelvin. So that's the temperature in Kelvin. Let's say for this cell it's 293. And let's say the cell is 0.1 molar sugar. If it's 0.1 molar sugar, what's our I value?
1.
1.
Yeah.
Because sugar is 1. Can you do this math and figure out what our solute potential is for this fictional cell we just made up? Do it right now. Plug in these numbers. -1 times 0.1 times 0.0831 times 293.
What was the mole concentrations?
0.01
0.1.
or 0.1.
Do you want me to tell you the answer?
Yeah, tell me the answer. Is
Negative 2.43.
that what y'all got? Negative 2.43?
Yes.
Is it a sugar? Wait, is that the water potential or the solute?
That's the solute potential.
So that's the pitchfork with the S?
Yes, that's this. So this value is negative 2.43. Is that what everybody's getting?
Yes.
Yay! Now we got to add that to the pressure potential. Normally your pressure potential is 0 if you're working at normal atmospheric pressure. And we'll say that this is all happening at normal atmospheric pressure. That means that that there's not a whole lot of stuff crammed into the cell to put it at high pressure, and there's not been a lot of stuff sucked out of the cell to make it low pressure. The cell is just operating at normal conditions. If that is so, our pressure potential will be 0. Normal water at normal atmospheric pressure has a pressure potential of 0. So we just add those two together, and what is our result?
Negative 2.43.
Negative 2.43. That's the solute. That is the water potential inside here. Negative 2.43. Now, what is the water potential outside the cell?
0.
How do you know it's 0?
Because it's 100% water.
Pure.
It's pure water. It's not going to take any water out of the cell.
Can you mathematically tell me it's 0?
Yes.
How?
You plug in 0 for it says 0.1.
Right here, C is 0. Did y'all know anything times 0 is 0?
Yes.
Pure water is always going to have a water potential of 0. Okay? Pure water is always going to have a water potential of 0 because it's 0.0 molar. So, here's the deal. Over here we have a water potential of 0. Here we have a water potential of negative 2.43. Water always goes from high water potential to low water potential. Water always moves toward the lower water potential. Since this is a negative number, it is lower than this number, so water is going to move inside the cell.
High photonic.
This is hypotonic. Less tonicity. So, you can determine how water will move. What if this wasn't 0.0 molar water? What if this was 0.1 molar NaCl?
You put a 2.
Go ahead and calculate what the water potential is over here. Let's say it's at standard atmospheric pressure. You plug everything into here, but it's NaCl. So you plug in negative, what's I?
2.
2. You change the I to 2. What's the C?
0.1.
Still 0.1. What's the R? It's
That.
always that number. What's the T? Let's say it's also 293. What do we get on this side?
Negative 4.86.
Negative 4.86?
Yeah.
So that's for the solute potential?
That's the solute potential, and since there's no pressure, it's also the water potential.
Wait, how can you tell if there's pressure or not again?
I'm telling you, there's no, we're
so
operating at
they'll say
atmospheric
it.
pressure. They'll say it in the problem. Y'all see what's happening here? If you put 0.1 molar salt on this side of the cell and 0.1 molar sugar inside the cell, which way is water going to go?
Out.
And
Oh.
into the cell. No, out of the cell.
Wait.
Water always goes from high potential to low potential. What's the lowest number?
Negative 4.8.
That's lower than that, so water's going to go that way. You can calculate the way which water goes based on these formulas. Isn't that cool? You didn't know which way water was going to go until you calculated it. Right? I mean, if I said that this was 0.3 molar NaCl, and I said that this was 0.5 molar sucrose, and I said that this was at 343 K, and I said that this was at 188 K, which way would water go?
In the cell?
You have no idea. You got to calculate, don't you? You got to plug in these numbers and calculate, and whichever one gives you the higher value, it's going to go the opposite direction. It's going to go toward the lower value. You see what I'm saying? It's that simple. That's all there is to this.
So would the 0.5 be plugged into the C?
0.5 is the C. 188 is the T. And the I is either 1 or 2 based on if it's sucrose or NaCl.
What if inside is the salt and outside is sugar? Then we would do, which one would we do then?
You calculate this, and then you
What
calculate
for?
that. You'll get two separate numbers. You do two
Okay,
separate
two different
calculations.
things.
You see what I'm saying? You'll get this number when you calculate this, and you'll get another number when you calculate that. Yes.
What would you put for the P?
For the P,
Water.
that's the pressure potential. Sometimes they'll tell you that the cell is under pressure and tell you to plug in a pressure potential of positive 5.6 or something like that. And you have to add that into your calculation.
Okay.
We're going to do some of those in a minute. I want you to try some of these first.
But if they don't tell you anything, you don't.
They'll tell you what the pressure is.
Okay.
Yeah.
So the cell is the solute, right?
The cell has a certain amount of solute in it. And they'll give you that in the question.
Alright.
Now hold on, we got to figure out what the units are. I has no unit to it. This is in moles per liter. C is in moles per liter. And R is in liter bars per mole K. Do y'all know how to cancel things out?
Bars per
Look, moles on the top and moles on the bottom, they cancel. Liters on the top and liters on the bottom cancels. Kelvin, the temperature is Kelvin. So Kelvin cancels with the Kelvin on the bottom, and you're left with bars. Bars is the unit of potential. The unit of water potential is in bars. So this unit in here is going to be negative 2.43 bars, and this unit out here is going to be negative 4.86 bars. You want to include the bars in your calculations. Sam, are you getting all this? Awesome. Zach, how's it going up there? Let's try a problem. You want to? Try the first problem here. Calculate the water potential of the following. 1.0 molar sucrose at 22 Celsius under standard atmospheric conditions. Standard atmospheric conditions means no pressure potential.
So then you would only have to calculate the water, the solute potential.
That's it. That's all you got to do. I'm going to erase this so it can make more sense. Hannah, are you already done?
I just on my calculator.
You don't? You want to use the calculator that is on your phone?
Oh, yeah.
Go for it. Look at you, I've got it on a sheet of paper. I'm going to take this up, so circle your answer, make it nice and neat where I can see your answer.
Can we just round to like the nearest 10 or hundreds?
You do as many significant figures as they give you in the problem. So if they gave you 2 significant figures here, your answer is in 2 significant figures.
Oh, right.
Does that make sense?
Yes, sir.
Wait, what?
Never go to more units that are in the problem. So they gave us 1.0, so your answer can only have 2 significant digits. Y'all didn't learn significant digits?
Well,
Bradford was just kind of like, oh, I don't care much.
It's very easy. So if they gave you 1.0 in the problem, right?
Mm-hmm.
So if you give an answer that's 2.353, you can't get. They didn't give you that much in the problem, so you can only give back what they gave you in the problem. So 2.3 you have to do.
Nope.
You see what I'm saying? That's all there is to it. Significant digits are easy.
What? God. Wait.
So
So if
It was just 100.
If it's 1.12, 1.1.
so
Yeah,
if
George.
it was like, say it was like 36.28, it'd just be
36.
36.
2 digits.
Wait, bro, can you
so-
explain it again?
so they gave me-
1.12.
Your answer was 1.12,
Oh,
You want me to tell you?
or they gave you 1.12 in the problem.
George.
No, they gave
Then
me
that's 3 significant figures.
yeah.
And you can give your answer in 3 significant figures.
So the most they gave
So,
us
bro,
was
what-
2, so I wouldn't have a decimal at all.
That's
I
right.
would just round
2
up.
figures, yeah.
What if the answer?
So if it
what
was
they,
like something 0.5, I would just round up to.
That's right.
What if they gave you 100? Just 100, no decimal point.
No decimal point, it's just 1 significant figure there.
So
If they gave you a decimal point, it's 3 significant
So will you accept? Wait. You go ahead. You go ahead.
so it was 100, and your answer was like 1,000. I mean, your answer was like 1.13.
1.13, you just call that 1.
1.
Yep.
Will you accept
Weird.
the longer answer though?
This is not the right answer.
All right. You don't have to worry that much about significant figures. They're not going to be testing you on that. They'll tell you how many decimal points they want. But it's really easy. Just put in your answer what they gave you in the problem. Okay, so what did you get for letter A?
Negative
24.5
bars.
Negative 24.5
Bars.
bars?
Shouldn't be negative 25.
It would be negative 25 since they only gave you 2 significant digits in the problem. So negative 25 is actually the correct answer. But the AP Biology test will tell you how many decimal points to give, so you don't have to worry about that. But it's just good to know your science. If they give you a bunch of decimal points in the problem, then you can answer with a bunch of decimal points. If they don't give you a bunch of decimal points in the problem, you can't answer with a bunch of decimal points. It's as simple as that. Do you want to hear a significant figures joke?
Yes.
Yeah.
Guy walks into a museum. He asks the security guard, how old is that dinosaur fossil? Security guard says, 70,000,008 years old. Guy says, how do you know it's 70,000,008? He said, because I've been working here for 8 years, and when I got here, they told me it was 70 million years old.
Uh huh.
Joke, isn't it? See, he's not using significant figures right. When they said 70 million, they were rounding that off, right? That's what's funny. Okay, let's skip all the way down. Did everybody get negative 25?
Yes.
Let's skip all the way down to D. Do letter D. 0.3 molar NaCl solution at 283 K at high altitude. Now they've thrown in a pressure potential. So you have to add the pressure potential in when you get your
C?
final answer. D.
D.
D. Do D. Duty. I said duty. My regular biology class, I thought that was funny.
It's pretty funny.
If they give you a temperature with 3 significant figures, then can you have 3 significant figures in it?
In your answer?
Or does that not make sense?
Yeah, you take the least number of significant digits that was in the problem. So do you see how that was 0.3? That's 2.
So it'd just be 2.
Yeah.
Okay.
It's actually 1 significant figure, but go ahead and put it in 2. Did you get an answer?
Yes.
Yes.
Wait, so how many significant figures does that be? 2?
Just put 2.
Wait, for YP, would you just plug in? Oh, never mind.
Uh-oh. We're out of time. What do we get?
Negative 15 bars.
Negative 15 bars.
Negative 15, negative 14.7?
Negative 1.
So, if you stuck, listen to this. If you stuck solution A next to solution D, which way would water move across the membrane?
Towards
The left.
A.
It would move toward A. A has a higher water, A has a lower water potential than D. It would move toward A. So try to work on these problems. They throw word problems in. It gets a little more difficult as you go. Work on this, your homework for tonight.
So no reading?
There's no reading tonight, no. I'm actually going to give you a few days to do this. Work on it some tonight. I'm going to talk about it a little bit tomorrow, and we're starting a lab tomorrow, so I'll grade these lab books.
Do you like half of it?